In this video, I will prove that every differentiable function must also be continuous. Or, as a formal theorem, given a number c and a function f defined at and near c, if f is differentiable at c, then f is also continuous at c. The converse is not true. There are some functions which are continuous without being differentiable. I will include a link in the description to some examples. As a reminder, saying that f is differentiable at c means that the limit in the definition of derivative at c, f of x minus f of c over x minus c, exists, and is therefore a number. And saying that f is continuous at c means that the limit of f of x, the function itself, equals f of c. Notice that these are two different limits. Before doing anything else, it helps to rewrite a bit the definition of continuity. Saying that the limit of f of x is f of c is equivalent to saying that the limit of f of x minus f of c is 0. This is because, for the purpose of the limit, the variable is x. F of c does not depend on x. It just behaves like a constant for the purpose of the limit. We can justify this more carefully if needed. If the limit of f of x is f of c, then the limit of f of x minus f of c will be f of c minus f of c, which is 0. And reciprocally, if the limit of f of x minus f of c is 0, then we can write f of x as f of x minus f of c plus f of c. The first piece has limit 0, the second piece has limit f of c, and they add up to f of c. So the two conditions are equivalent. I will keep the second condition rather than the first. Now that we have agreed on definitions, let's explore the relationship between differentiability and continuity. If f is continuous at c, let's see what happens when I try to compute the derivative f prime of c as a limit. In the numerator, I get 0, and in the denominator, I get 0 as well. I get 0 divided by 0, which is an indeterminate form. It means I have to do some more work to figure things out. In some cases, this limit will exist, in others it won't. So the derivative f prime of c may or may not exist. By contrast, if f is not continuous at c, when I try to compute the derivative f prime of z as a limit, I get not 0 divided by 0, so to speak. This limit will never exist. In the best case, I could get a non-zero number divided by 0, which may be plus or minus infinity, but the limit does not exist. Okay, this was not a rigorous proof, but I find this argument simple and convincing. It explains why, if a function is differentiable, then it must be continuous as well. But we can do better. We can write a formal proof. Let's do it. Assume f is differentiable at c. Then, I write the limit of f of x minus f of c. I multiply and divide by x minus c. Now I have the product of two functions, so I use a limit law, and the limit is the product of limits. The first limit I recognize as the derivative f prime of c, and the second limit is 0. So the product is 0. A very important remark. I am not saying that 0 times anything is 0. I am saying that 0 times a number is 0. To use the limit law, I needed both limits to exist. The first limit exists because I am assuming f is differentiable at c, otherwise I would not be able to use this argument. And now I have proven that the limit of f of x minus f of c is 0, which means f is continuous at c. And that completes the proof.